Yes, welcome to our lecture fact. This is our 11th lecture, and uh, we are going to discuss the transient stability with the help of improvement of transient stability with the help of shunt fact controller. So before going to application of shunt compensation in the transmission line for improvement of the transient stability, first, we will take the review of transient stability so that it become easier to understand the shunt compensation in the transmission line for improvement of the transient stability. So there are two type of fault. Fault can be categorized as a one fault, or it may be say is a perturbation or disturbance. It is the slow disturbance. And second is a large disturbance. Large disturbance. This disturbance may be the change in load. Say, for example, that there is a daily load. We know that the historical data for the change in load. So this change in load comes under the slow disturbance, because we know the power is the demand is going to increase in the evening time. The demand is going to decrease in the from 6:10 p.m. to morning 6 a.m. But the large disturbance is considered as a sudden change in the load, unexpected change in the load. There may be a failure of one of the generator, 100 capacity or more than 100 megawatt capacity generator suddenly trip out. It may be the application of fault in the transmission line. It may be a 132 kV transmission line, or say 220 kV or 400 kV transmission line. If this such type of fault is occur, it comes under the large disturbance. And because of large disturbance, there is a transient in the system. So the transient in the system, say for example, this is the two diagram is there. This diagram is nothing but the mechanical power input to the generator. This is generator and this is prime mover. The mechanical input is remain constant. It is generating, it is supplying to the infinite bus. The excitation voltage is EF at an angle of delta, and current is IA. So we can say that the power P is equal to EF terminal voltage divided by reactance into sine delta. This is the power it is going to deliver by the generators, isn't it? Now, whenever there is a change under balance condition, the mechanical input and electrical output is same. Or if you just consider that there is no losses are there for our simplicity, your mechanical input is equal to the electrical output, and generator is running at the constant speed or synchronous speed. Now suppose suddenly you have increased the load on the generator. What will happen? Or we can say that suddenly the mechanical input of the generator get increases. So there is a change in mechanical input, and because of change in mechanical input, there is a change in speed, and hence there is an unbalance between mechanical input and electrical output. And because of this unbalance, there may be acceleration and there may be a deceleration. And it is that whenever there is a change, whenever there is a sudden change or transient condition, the equation, we can say that the equation is described, which is equal to m d square delta upon dt square is equal to PA, or which is equal to the difference of mechanical input and electrical output. There may be a difference. It may be a more electrical output is there when the load on the generator is suddenly increased, and when mechanical input is more, when there is a change in mechanical input is greater than the electrical output. So this is called as a swing equation. Swing equation. Here, I'm not going to explain each and every derivation of the transient stability. Just to understand the transient stability and improvement of transient stability with the help of fact devices, we are taking a review of transient stability. So now it can be explained as with the help of some P delta curve or power angle characteristic. From this equation, we can draw, this is the power P, and sorry, this is the, yes, this is the power P, active power, and this is angle delta. And this is can be represented by, it is P delta equation and curve is there. It is going to become maximum at this one value. So this is the maximum power. This is the maximum power. But we never operate our system at the highest point because in any case, the system may come out from the synchronism. So this part is the instability, whereas this region is a stable region. So we will operate our system under the stable region, means the leftmost side of this one. Say for example, the system is operating at this point where mechanical input and electrical output is same. So here this is mechanical input, and here is the electrical output. PE is the electrical power. PE is the electrical power under the angle delta 0. So this is the initial angle. Let suddenly the mechanical input has been increased. Somewhere the mechanical input is increased. So what will happen? There is a acceleration. So generator will accelerate, and due to this acceleration, the generator frequency, slightly the frequency will be more, and to settle to the new equilibrium position, the angle is going to increase, and again the mechanical angle is going to decrease, and somewhere after some time, or means 2 or 3 cycle, it is going to settle to a new equilibrium position. So now this is called as a acceleration. This is the acceleration area, and similarly the area under when it is swing to its maximum value, this is say the maximum angle at which the generator is going to swing. So it is called as a deceleration area. So when this angle, when this area A1, say this is area is A1, this area is A2, acceleration area and deceleration area become equal, the system come to the stable one. So it can be represented as this one is a time, and initially this is the angle at which the system is going to work. Suddenly the load changes or the mechanical input has been increased, it will oscillate, and after some oscillation it will settle to the new equilibrium position. So this is the delta 1, whereas the maximum swing, this one is the maximum swing, is the maximum angle, isn't it? So the transient stability, there is some assumption which is called as a classical model, in which the system is going to assume that after the system is going to judge by the first swing, if your second swing, this is the second swing, is smaller than the first swing, the generator or the system is going to stable at some value, isn't it? So 1.5 cycle, it is called the steady under 1.5 cycle is called as a transient stability study. So it is quite clear. Whatever the transient stability is, that we are going to consider 1.5 cycle, and after 1.5 cycle, the system is going to settle to the new equilibrium position, and the way or the tracking to its final value, it is called the brief period during which the system settled to the new equilibrium position. It is called as a dynamic stability. So there are 3 types of stabilities are there. One is the steady state stability, second is the transient stability, one is the steady state stability, second is a transient stability, and third is the dynamic stability. So steady state stability is the stability where the change in parameter or the change in mechanical input, there may be a change in electrical power, is slow and small. This steady comes under the steady state stability. The transient stability is the sudden and large disturbance. This sudden and large disturbance is going to cover in the transient stability. And the way of tracking to its final position, that brief period, is nothing but the dynamic stability. So our interest here, our area of interest is the 1.5 cycle, is the transient stability, and it is going to calculate from this swing equation. This is the second order differential equation. So we can go by calculating some numerical values, numerical method for calculating the value of delta. Either the system is stable or not, or there is some graphical method. That graphical method is called as a equal area criteria. So here the criteria become is that if the area under acceleration and area under deceleration is equal, the system is going to stable. Okay, so this is from this equation. That is, what is that equation? It is the equation, swing equation, where m d square delta upon dt square is equal to PA is equal to mechanical input minus electrical output. When this system is stable, when mechanical input is equal to the electrical output, the system is stable. The acceleration will zero. So generator neither accelerate neither decelerate, and the system is stable. So we can say that here, the for steady state, for the transient stability, the acceleration power should be zero. And we can say that from this equal area criteria, the area under acceleration curve, either it may be acceleration or deceleration, both. So area under acceleration, delta 0 to its say delta maximum, integration PA d delta is equal to 0. Means the acceleration power, the area under acceleration curve should be equal to 0 value. Then the system is stable, and this is called as a equal area criteria. And the transient stability is judged with the help of equal area criteria. Now we will take some few example to understand the equal area. This one, say the system is there, a generator is there, and it is connected to the infinite bus. Just we have seen the terminal voltage, excitation voltage EF at an angle of delta, it having some reactance and delivering the current IA. So we can represent, definitely there is a mechanical input, and mechanical input during transient condition remain constant. So whatever it value, because whenever there is a fault on the electrical side, it cannot be sensed in the same period. So there will not be any change in mechanical input. So in the classical model, we are going to consider, or we are going to assume some points. One is that during transient, mechanical input remains constant. Second, we can say that the transient stability is judged by first swing only. If your second swing is smaller than the first swing, the system is stable. Or if your second swing is greater than the first swing, say here, it is greater than the first swing, there may be a chances that the system is unstable. So this is the instability. Therefore, it is going to judge by the first swing. Now from this one may draw this diagram. This is the power P. This is the angle delta. This is the angle delta, and this is the power P. And now It is the P delta curve. Let our system is operating at this point where the angle is equal to delta 0. Okay, here mechanical input is equal to the electrical output. Now suppose suddenly the fault occur over here and the power P goes to the 0 value. No doubt here the equation is same which we have already considered. P is equal to EF Vt upon X into sine delta. So when the power goes to the 0 value, this is the operating point initially. This comes over here. This is the fault occur, and because of fault, if the fault remains there or present, after that the circuit breaker is going to open. So again, your generator, because the electrical power is 0 and mechanical input is remain constant, so generator is going to accelerate. So during this time, up to the clearing of this one, the generator will accelerate. So this area is called as a acceleration area A1. And once the power is again connected or the system is say healthy condition, again it will take the power, but suddenly when the load is increases over the generator, it's going to decelerate. So this is the deceleration area. This is the deceleration area A2. So A1 is the acceleration area. A1 is acceleration area, and whereas A2 is the deceleration area. Okay. And what is the A1 area? A1 can be write as this is the what we can say that integration delta 0. Okay, it is from delta 0. So say this is the delta CR, critical resistance, at which just we will have some comments over the critical value. DCR is equal to mechanical input PM minus 0 D delta. Here we are not going to consider the calculation and integration on these things. Similarly, area A2, which is equal to area A2 is equal to, it is start from delta CR, critical value of the angle, and this is up to this, say, delta maximum, delta maximum, which is equal to power at any point over here, which is equal to the P maximum into sine delta minus PM D delta. So this is the area we can find. So what are different value? This is the P maximum. This is the P maximum. And at any point, this is we can represent as P maximum into sine delta. Anywhere over the curve. And what is delta 0? Delta 0 can be represented or can be calculated from this equation, simple this equation, EF Vt upon X into sine delta 0, because it is the initial condition. So from this sine delta 0, or P is equal to P maximum into sine delta 0, so we can calculate the angle delta 0. Once we know the value of delta 0, which is equal to sine inverse of P upon P maximum. Okay. Once we know the value of delta 0, the P maximum, delta maximum is equal to this is D maximum, delta maximum, this maximum angle. What is that? This is the intersection of mechanical input line. This is same because the curve is symmetrical one. So which is equal to pi minus delta 0. So in this way, we know each and every point. So we are able to calculate the value of delta CR. What is delta CR? Delta CR, it is the critical clearing clearing angle. Now, this is our point of interest. What is point of interest? Say, for example, if the circuit breaker is going to open, or it will take more time to operate, operating time of the circuit breaker is greater, it is going to open over here, isn't it? Now, look at this figure very carefully. Now, the area A1 is larger and area A2 is small under such condition. So, what happened? Area A1 is greater than area A2 and system will unstable. Okay. The system is going to stable only when area A1 is equal to area A2 or system is stable. So our stability criteria for the transient stability is that when acceleration area is equal to the deceleration area is same, or your deceleration area is greater, the system is stable. Otherwise, the system is going to unstable. Okay. So it means that in our requirement is that we should have more deceleration area. Our objective is to increase the deceleration area. Say, for example, we consider a second case in such a way that this is angle delta and this is power P, and this is the curve, P delta curve, and system is operating over there. So no doubt this is the maximum power. This is the mechanical input is equal to the electrical output. Here it is delta is there, delta 0 is there. Okay. Now, if your circuit breaker is too fast, it is going to open over here, and somewhere the deceleration area also become equal to the acceleration area, and system will stable. So this is the clearing angle, and this is delta 2 or delta 1 is there. So this is the margin. This is the margin for transient stability. Transient stability. It means that if you are able to reduce the acceleration area is one thing, or either we can increase the area, this one A2 area A2 by some means, by using fact controller, by using some other method, then we can improve the transient stability, isn't it? Say, for example, there are different cases are there for the transient conditions or transient stability studies are there. For example, this is the supplying end or source is there, and there are two transmission line. When there is a two transmission line, there are two reactances are there, and it is going to supply to the machine 2. Okay, we are restricted to the machine 1 and machine 2. Under such condition, this is the reactance X1, this is the reactance X2, or let the reactance X1 is equal to X2. We can say that the maximum power or P is equal to EF. Say this is EF, this is VT upon equivalent reactance X equivalent into sine delta. And definitely the X reactance is smaller than the single line resistance or single line reactance is there. Okay, so under such condition, what is that? It is the system is more area, or this is the curve, it is P maximum. Okay, now suddenly the fault is occur over here. The circuit breaker is going to open and power is going to transmit during the fault condition, the power reduces to the small value. Power reduces to the small values. Okay. And now the circuit breaker is open. So the power is going to transmit by a single line. As the power is going to transmit by the single line, under such condition, this is the curve under single line, isn't it? Because why it is smaller? Since the reactance of one transmission line is greater, so this is the P maximum 1, this is P maximum 2, this is the P maximum into sine delta, it is the 2, okay, and this is P maximum 3 into sine delta at any value, okay, and this is P maximum 1 into sine delta. So under such condition, the equal area criteria, say initially the system is operating over here, okay, so this is the acceleration area during which the system is going to accelerate and it is going to decelerate because this is 1. So this is the A1 area, acceleration area A1, acceleration area A1, and this is acceleration area A2. This is acceleration area A2. Now see here, again the acceleration area A1 and A2 is very close to each other. The system may come out from the synchronism because it does not find to reach its maximum value, isn't it? Or the area A2 may be smaller and the system will be unstable. We have installed auto reclosing. We have installed one auto reclosing system. Auto reclosing system. The meaning is that suddenly after one, because the most of the fault on the transmission line are transient in nature. It may be because of some conductors are going to touch, or it may be a wind because of wind or bird falling is over there. So once the system or the circuit breaker closes, again it reach to its previous condition. So now, suppose it is reaching to its previous condition, we will find more area A2 as compared to the previous case. So this is the case. So this is one is the area. Okay. This one is the area, this one part. And again, this additional area we are going to find out. And definitely this area A2 and A3. So your A1, definitely A1 is there, is the acceleration area, whereas deceleration, this is the acceleration area, and whereas A2 plus A3 is the deceleration area. And definitely under such system, the system definitely goes to the stable one. So the improvement in transient stability is also done with the help of auto reclosing. Now we will try to see some PPTs are there. Just we will go to the very fast. This is the system is there, in which this is the mechanical input. Okay, and this is the generator. Under normal condition, the mechanical input is equal to the electrical output and system will stable. This equation is used to drive the swing equation, and this is the swing equation. This is our swing equation. M d square delta upon dt is equal to acceleration power, and acceleration power is under normal condition is 0, but whenever there is a sudden change or either the change in mechanical input or change in electrical output, the acceleration power comes into the existence, and this maybe accelerate or decelerate the generator. So this is the swing equation. Okay. Now our there are, for understanding the transient stability, there are some assumptions. This assumption is that the mechanical input remain constant during the transient condition, damping or asynchronous power is negligible, and so on. Say transient stability is judged. This is the very important, is by the first swing only. Now Transient stability is judged, very important is transient stability is judged in the first swing, constant generator main field and constant mechanical input, which we have considered over here. Now this is the important point, Excel. This is our area under acceleration. This is nothing but the acceleration. It is represented by angle delta. So this is acceleration power, this is deceleration power. This acceleration and deceleration power becomes zero, the system is stable. So delta 0 to delta, this is delta 0, okay? Delta 0 to delta maximum, the acceleration power should be 0. So this is our equation, P delta 0 to delta, P delta, PA is the acceleration power with respect to delta, it should be 0, the system will be stable. Now here, the sudden change in mechanical input consideration, one example has been taken. This is the generator, it's the mechanical input, it is connected to the transmission line. Under such condition, again, this is the P delta curve. This is P delta curve. Initially, the mechanical input is PM0. Suddenly, the mechanical input has been increased. Because of the sudden increase in mechanical input, definitely the generator output is smaller and generator input is more. Generator is going to accelerate, its speed is going to increase. So this is the acceleration area. And because of this one, the generator is going to swing, and it is try to find a new equilibrium position, and it will take some oscillation. So here, the synchronous speed, the speed of the alternator, speed of the generator is going to increase more than synchronous speed. See, it is omega is greater than omega s. So it is the synchronous speed. This is the synchronous speed, and this is the speed of alternator. So alternator speed is more. Now again, the speed of alternator goes to the smaller value, smaller than the synchronous speed. So it will take some time to settle a new equilibrium position. And if the acceleration area and deceleration area become equal, the system is going to stable at a new equilibrium position. Otherwise, the system is going to unstable. So here, in this case, it is quite difficult to find the value of angle delta 2. So instead of taking the delta 2, we are taking the maximum angle over there for our calculation purpose. Here, say this is the PM. So we can find this angle. Okay, what is that angle? It is the maximum power here, whatever this intersection, because these two intersections are symmetrical. So once we know the value of delta 1, it is quite clear. It is equal to delta 2 will be equal to pi minus delta 1. So we are taking the entire one, and by calculating this one, we can say that what would be the value of delta, okay, or new equilibrium position. So this is the case. So say here, this is the one also. Let the fault is occur over here. Let the fault is occur in this case. But as soon as the fault occur, the power goes to the 0 value. So here the power, initially it is operating at point A. It is supplying power. P is equal to, power is equal to P maximum sine delta. What is that? This is the delta 0. Okay. So this is now the fault clear, and area A1 become equal to the area A2. But again here, delta 1 is quite difficult to calculate. So we are taking its maximum value. And from this maximum value, again, the delta maximum is equal to pi minus delta 0. So it is the way to calculate the value. Okay. So this is the area A1. This is the P maximum is equal to pi minus delta 0 to delta CR. This is the critical clearing angle. Isn't it? Is we have considered this is the maximum angle at which the system should be open. If it will take more time, definitely the system come out from the synchronism. Therefore, it is very important to set your circuit breaker. Total operating time of the circuit breaker should be smaller than the time required to become area A1. So what is it is called as a critical clearing angle, and the time calculated from this equal area criteria, it is a critical clearing time. So the circuit breaker time should be smaller than the critical clearing time, which has been determined or estimated from the equal area criteria. So area A1 from delta 0, this is delta 0 to delta CR, maximum is the, so this is the values PM minus 0, means from PM to 0, d delta, this is the area A1. Similarly, area A2, it is start from delta CR to delta maximum. So delta CR to delta maximum. At any point, this is the same maximum. It may not be maximum somewhere. So we have taken the maximum value into sine delta minus mechanical input. So upper region, and we can find the area A1. So if area A1 and A2 is equal, then the system is stable. And we are able to find the critical clearing angle. This is the critical clearing angle by which it is the maximum value of angle at which the system is stable. Similarly, we can find the critical clearing time. So this is the critical clearing time. Our circuit breaker time should be smaller than the critical value. Otherwise, the system is going to unstable. Okay. Now, this is the case which we have considered. There is a two parallel lines are there, which having the reactance X1 and X2 is there. For our simplicity, we take the value of X1 and X2 is equal. Under there is three curves are there. So this is three curves are there. It is pre-fault condition. It is the during fault. This is during fault. The power reduces to the small value. And once the fault is clear, means one of the transmission line circuit breaker get open, the power is going to transmit, the system is going to transmit the power by a single transmission line. Therefore, the power transmitted capacity will be smaller. So it is the post-fault condition. So it is by the two transmission line, it is during fault condition, and it is power transmitted by the single transmission line. So now again here, it is possible to calculate the area A1 and A2, or the maximum value we can take for our calculation purpose. If your area in A2 or acceleration area become acceleration area deceleration, the system will be stable. Our objective for the FACT devices is to increase that area by some means. This area, our objective is to increase this area. Okay. So we'll see in the next lecture the application of FACT shunt compensation for improvement of the transient stability. Just we are going to, we are taking the review of transient stability. Okay. So by this way, this is the, we have taken the maximum angle and we are calculating with the help of this some calculation, their integrations area. Now auto reclosing. Auto reclosing, many of the faults are transient in nature, and if it is reclosed, many times the system get restored, or this is the usual practice in the power system to take one or two, maximum two, say chances, either the system become maximum one. So what is the advantage of the auto reclosing? Here, see, this is the auto reclosing. Under a fault condition, this is the acceleration area. The generator is going to accelerate. This is the acceleration area. Okay. Our objective is to increase the deceleration area. So now, during fault condition, once the fault is clear, when the fault is there, that power is transmitted by the single transmission line, and it will give the deceleration area. But here, your auto reclosing means your circuit breaker is reclosed. So again, the power transmitted by the second transmission line also. And we are getting this much is the additional area in deceleration point. So what is the deceleration area? A2 plus this A3 is the deceleration area. And hence, the system, we have some marginal deceleration area. So this is called as a marginal area to make the system more stable. So now this is our margin. So we may increase our mechanical input and the system may operate at a higher angle as well as at a higher power delivery. So here the power delivery will be small, operating angle will be small, but as we are able to add some marginal area, we can operate our system to a higher angle, and power transmitted by the transmission line or the system is get increases. So by increasing the deceleration area, our objective to deliver more power, or there is some more margin, more stability limit for the transient stability. So this is the say what we can say, that it is the some basic review of our system transient stability. Now this review we are going to apply for the shunt compensation. Thank you.